Okay, all right, good. All right, let's go ahead and get started. So, there's an introduction. Oh, sorry. There's a slide that I've got to find. Sorry. I'm using my own branded deck. I should have done it in, sorry, actually, let me move across to the Moov one. The template they sent is not a template, and so it took me a long time to move everything over to the PowerPoint version. So I'm going to do the PowerPoint one, that's where I'm expecting. Sorry, just give me 30 seconds here. Here we go, all right, let's try that. That's going to work a lot better. All right, now I've got to find the slideshow. There we go. All right. Thank you, everyone, for attending my talk. So my name's Tim Faulkes. I am the Chief Developer Advocate at Aerospike. I've been a developer for more decades than I care to count. I think I wrote my first computer game when I was 11. I've written financial services applications. I've done a whole bunch of things, typically large database-style problems, real-time distributed systems. So I'm a geek. I've always been a geek. I will always be a geek. The genesis of this talk was I've been a developer long enough that I mentor other developers. I show them how to do things and stuff. And what I'm finding is with AI, there's so much jargon and mysticism around it that more experienced developers like myself have heard the things, but we haven't had time to learn about it. And it's like, well, what is an LLM? What's a RAG? How do they interact? How do they hang together? And so I figured that I'll take the time to learn about it so I can tell you guys about it. So if you're in the same boat as myself as an experienced developer, these terms will now have meaning for you. Hopefully by the end of this you'll be able to say, yeah, I understand what these mean. I understand how they hang together. And at least have a good understanding of what AI is and how to use it. We are going to develop a LLM and we're going to make a chatbot in this talk. I've already written the code, so I'm not actually going to do it live because I'd screw that up. But I'll show you the code, we'll go through it, and you'll see it's really not magic. And vectors, I did some research on the internet and people said, vector, well, it's this magical thing, and you put your text into this thing and you get these numbers out. And I'm like, what does that mean? That doesn't help me. So hopefully this talk will be useful to you if you're in that boat. If you're an experienced AI developer, you ask the hard questions, but you probably won't get a lot out. But if you're sort of newish to it, that's really the audience I've intended this for. I'm going to encourage you to ask questions as we go through. So shout out if I've got some squishy things. If you ask a good question, I'm going to throw a squishy thing at you. If you don't want it, throw at your neighbor. They're really soft. They don't hurt. My aim's really bad, particularly with the roof. Yes, you've already got one. This is good because there's no way I'm reaching that. I tried to throw one to the gentleman in the back. It almost hit someone 2 rows in advance, so this is perfect. All right, so ask questions. All right, so the first thing I want to talk about is large language models. We've probably all heard of these. I'm going to refer to them as LLMs because it's a lot easier to say than large language models. Oh, the other thing I need to say is I'm Australian. I have an Australian accent. When I get passionate about something, I get excited, I talk faster. If you can't understand me, please shout out and say, could you slow down or repeat that? It won't be offensive at all, I promise. So, what is a large language model? It's an artificial intelligence algorithm, as we know, that uses deep learning techniques and massively large data set to understand, summarize, and generate new concepts or new content. So something like, can fish breathe underwater? You type that into your ChatGPT and it gives you a response and say, yes, they can. But how does it do that? I mean, a computer does not naturally understand English. It doesn't understand whatever language you're using. So what it's doing is it's breaking those words down into tokens. Now the token is something like 0.7 of a word. A small word might be 1 token, 2 small words next to each other might be 1 token, or a big word might be half a token or something like that. It might have a couple of tokens per words. And then it does calculations. It runs through a neural network and does a whole bunch of calculations. Even just getting the computer to understand the first sentence, can fish breathe underwater, is probably doing billions and billions of computations behind the scenes. So is forming the result on the other side. So there's a lot going on there. One of the things that really struck me when I started my AI journey was this concept of prompt engineering. When you are programming an LLM, you've got the input from the user, but you also have to tell the LLM what you want it to do. And the way you tell it what to do is by giving it context. And so you give it these instructions which, instead of programming it and saying, hey, I'm going to write some pseudocode or some real code which will actually tell you what to do, you tell it in English. So these, someone didn't tell me that I'm on the wrong screens. Okay, sorry, let me try that again. Present view, and how do I swap screens? Yeah, okay, I can't see from this angle. Tell me when I'm near it. That one? Thank you. Right, I apologize. I wish someone had told me that. Okay, I'm Australian and you can't offend me. If you shout out and go, hey, Dumbo, you've got the things on the wrong screen, that would be appreciated instead of just letting me blithely go forward. All right, so these are two very different prompts that I put in into the same LLM. The only thing I changed is what I asked it. So one was, I said, you're a happy chatbot designed to answer the following question in a whimsical manner. Do fish breathe water? Oh, sorry, do fish breathe air? And you can see it's gave me some nice, happy, sort of light and fluffy information. And then I said, you're an angry chatbot designed to answer the following question in a gruff manner. And it gave me a very different answer. The same material is there, but the manner of which it has responded is very different. So how you get it to answer the question is really important. This prompt engineering is something that really surprised me because we're telling it in English what we want. So when you hear of what, if someone says they're a prompt engineer, that doesn't mean they're punctual all the time. It just means that they design prompts for AI to actually be able to do this sort of stuff. And it makes a huge difference. All right, so let's talk about using LLMs because we're developers. Everyone here a developer? Anyone not a developer? Okay, good. We're technical people. We want to know how to write these, okay? And I'm like, oh, these are going to be really complex. It turns out they're really simple. So all my examples are going to be in Python. I'll give you a URL to this repository so that you can see all the code later. It's all open source. The first thing I want to do is I'm using a model called Gemini Flash. It's a Google model. I'm actually running it on their managed service so that I could run this on my laptop if I wanted to pick a different model. The problem is my laptop doesn't have a strong GPU. And as I said, these things are doing billions and billions of calculations. So if I ran it locally, it would be very, very slow. If I run it on the service up there, then it's really quick. And it's really expensive to run it up there. I think I've spent 18 cents on all my preparation of doing all this stuff. So it's actually pretty good. So first thing I'm going to do is I'm going to do a few imports. I've downloaded a couple of libraries and I've done some imports. And I've given it my credentials and said, this is who I am so you know who to bill. Once I've done that, all I need to do is create a generative model and tell it what my model name is. I'll talk more about where you get these model names from in a moment. And then tell it what my prompt is, or my question, and say start chat. That's literally all you need to do. So let's have a look at this in action. So if I look at my Visual Studio Code, I've got an LLM. So this is, everyone can see that? Is that large enough for people at the back to read? Yep. Okay, so this is the code I'm going to be running. I'm happy to change this. If anyone wants me to change this up, I've said, hey, I'd like you to answer with a rhyme. Does anyone want me to change this to something else? Tell you what, let's go crazy with a, let's see, haiku. Let's try and save that, and then we're just going to run Python LLM. I love doing things real time because who knows what this is going to produce. Okay, it's done a half reasonable job. Water, silent breath, gills, filter, lice, sweet nectar, no lungs needed for air. I'm sorry, 10 years ago, if someone had told me that I could write a program in, 6 lines of code, that could actually do something that could not only interpret English, but be able to generate a haiku out of the end of it, I would have called them crazy. But it's really easy. Getting started in this stuff using Python is really, really trivial. All right. So, LLMs are really good. We can see how easy they are to use. They suffer from some problems. An LLM has been trained. So if we look at, say, ChatGPT or Llama 2 or any of the common LLMs, they have been trained on a data set. Now that might be, say, 10 terabytes of data is not an uncommon data set to be trained on. And that data set existed at a point in time. Therefore, the knowledge that LLM has only exists at that point in time. Anything that was created after that point in time, it can't answer because it knows nothing about. So the data can get stale. Their responses can get stale. They can also be, they're very specific, they're very general. These can answer questions on almost anything on the internet, but they can't look at your company's internal documents and answer questions on that. They weren't trained on those. So they're very agnostic. They are not specific to your domain. They're also prone to hallucinations. Now, I know many people know what these are. For those who don't, it's you ask it a question. So in my case, I've said, how do I create a secondary index in Aerospike? And the answer it's come back, sorry, I work for Aerospike in case it's not obvious. The answer it came back is indexes in Aerospike are created using the secondary index administration tool. I've been here for 8 years and I have never heard of the secondary index administration tool in my life. It is a total hallucination. It has made stuff up. So, this is bad. If you can't trust the results of what it's telling you, and whenever you use an LLM, you'll see down the bottom it typically says things like, the content might be inaccurate and it might just be plain wrong. They put caveats around that. So what can we do about these? There's a couple of solutions that I'm going to discuss. One is fine-tuning the LLMs, and the other is doing a retrieval-augmented generation. But before I do that, let's go back to another demo. So we want to, okay. I'm going to create, I've got a chatbot window. Let me bring up my chatbot. All right, so this is what we're going to use as the chatbot. I can be able to type in answers and get, questions and get answers as a result of this. So what I'm going to do is in my code, if I look at this, I've got, this is my chat. It's going to come in here whenever I type something in, and it's going to form a response. Now, in this case, I haven't given it anything else. I've just said, form a response with no VectorDB. In this data set that we have helped create, I have put a base 20 products. I haven't loaded the products that you guys have created in yet. But at the moment, I haven't told this LLM about those products at all. This data set is obviously created after this LLM was coded. So I'm going to ask it a question, what products can griffins use? Okay, and it's going to come back and say, actually let me say, what products, you've got to be very careful about what you ask, what products do you have for griffins? Okay, now it's come back with some products. So the Golden Claw savings account, the Griffin credit card. Okay, well that's savings account. Let's have a look under our savings account and our bank products. There is no Golden Claw savings account. In fact, if I looked up each one of these things that it has come back with, they don't exist. Not a single sentence on this screen exists in the database. It is a pure hallucination. It is basically made up stuff. My teenage sons do this on a regular basis. They treat it as fact and say, yeah, this absolutely is. And I look at it and go, But anyway, so if I look at this, when I've asked this, I've given it a prompt. And the prompt, I have to find up here. So this is the prompt I've given it now. All I've said is, you're a helpful assistant answering questions on the Creatures Mythology Bank. It offers banking services. Answer the question. What I'm going to do now is switch it to a slightly different prompt. It's got the same sort of information, but at the end it said, using only this information, answer the question. If you're unable to answer the question, ask for more information. So what I'm going to do is I'm going to come back here, and I'm going to say, where I tell it, sorry, the nerves of standing in front of people means that I can't find the code. Where's it gone? Okay, that's the streaming one. Here we are. Okay, so I've used that hallucination prompt. So I'm just going to change my streaming response to use no hallucination. And you can see that this is this stream response is going and calling the LLMs like we mentioned before. So I'm just going to save that. I will copy this same question, and I'll reload that. And if I ask the same question, now what it's done is it's given me a different output. So it says, I don't have enough information. The information doesn't specifically mention which products are available to griffins. So we've stopped some of the hallucinations by giving it a more complete prompt, by giving it more instructions which say, if you don't know, don't make up stuff, just tell me you don't know. I'd much rather that. Tried that with my teenagers too. It didn't work at all. So LLMs have something over my teenagers. All right, so let's go back and have a look at the code again. So if I find PowerPoint, it's over there. Okay. All right, so let's look at how we can help it reduce these hallucinations. So there's two techniques we're going to use. I'm going to talk about. One we're going to use, one we're not. The first is fine-tuning these LLMs. So what has happened that we've discussed so far is we've got this publicly available data set. It's called the internet, and people have trained databases or these LLMs on that data set. So they've created these foundational LLMs. They're the ones we tend to use. They're the ChatGPTs and similar. If we want, as an organization, we can go and fine-tune those to particular domains and optimize them for specific purposes. So this tends to fall in the realm of the data scientist. What they need to do to form this labeled data set is quite extensive. They need to go and create a set of data. Now, that data is typically thousands to tens of thousands of items. They need to be labeled. It needs to be very domain specific. Retraining the LLMs takes time. So this process isn't something you want to do quickly. So a good use case for this is, I'm in the legal domain. I don't want it to answer in English. I need to answer it in legalese. So that is something that you might fine-tune an LLM for. This is something that is slower to change. So it can't respond to things in real time. It's harder, but it means that something like that language, using legalese, is able to be answered by an LLM. It is also faster. Remember that these LLMs are doing billions and billions of calculations every time you ask it a question. If it's got a more focused and specific set of information, it needs to do less work. So a finely tuned LLM offers some advantages, but they're harder to get than using RAG. So the more common one, the one we're going to focus on here, is using Retrieval-Augmented Generation. This is always using that generic LLM. And what we have here is two things that happen ahead of time. Firstly, the publicly available dataset trains that foundational LLM. But second, we are going to use vectors. I'm going to talk about what vectors are in a moment, but a vector is effectively a set of numbers. It's an encoding of information down to a set of numbers. Think of a JPEG algorithm. It's a lossy algorithm. You can't get back all the information. It's taking high-resolution images, turning it into something smaller. It represents that, but you can never get that information back. So in our case, we've got products in our bank. What we're going to do is we're going to encode each one of those products in the bank using an embedding LLM. It's a different LLM, but it's still got the same sort of concepts. The only difference is, instead of producing text, it's going to produce a set of numbers, a vector. And the same LLM can always produce vectors of the same length. So for each one of my products, I'm going to run that through my embedding LLM and get a vector out. When we go and ask it questions, my user is going to put something in the prompt, and it's going to ask the LLM to encode my question as well. And note that it's the same LLM. There's no point me encoding my data with one LLM and encoding my question with a different one. It will not work. So once we've done that, we're going to get a vector out. Okay, so now we've got a vector which represents our question. We've got a whole set of vectors which represent the information in the database. We're going to use a vector database to do a search and say which one of these vectors is most similar to those other vectors that I've passed you. And the results will come back out. Not only will it give us the vector, but it'll give me the information that was encoded with it. That's important because a vector has no meaning. You can't go from a vector back to anything meaningful. So you store the vector with the data that was encoded to form the vector. You take that data, you pass all of that information to the LLM, and it stops hallucinations. It gives you much better things. So this is where developers come in. The other one is data scientists, fine-tuning LLMs. As developers, this is the area we will focus on. All right, so let's talk about vectors and semantic search. I'm going to drill into details now. Because when I looked at this, when I did some research on vectors, there's so much stuff on the internet which says a vector is, well, you take your model and you put it into this LLM and it gives you a vector out. I'm like, what does that mean? How does it do that? What is it doing? So we're going to go through a really dumb example. Okay? But fundamentally, an embedding model, the LLM that does the embedding, takes your information. It doesn't have to be text. It can be images, it can be video, it can be audio, they can be multimodal. Transforms them into a vector which is just a set of floating point numbers. It's a linear array of floating point numbers. So I'm going to dumb this down so that even I can understand, and I'm Australian, so if I can understand it, you guys will have no problems whatsoever. Let's say we're buying a house. We have a target that we want a house which has about 2,500 square feet of floor area and about 6,500 feet of land area. We know that we won't find that exactly, so perhaps to us the floor space is twice as important as the land area. There's 9 houses that we're interested in. And you can see the details of the land area and the floor area here, and here's a graph of them. So this red X is what we're aiming for, and these other blue points are what we're trying to do. They're the other houses that are in the neighborhood. All right. So the first thing I'm going to do is I'm going to turn each one of these houses into a vector. I've only got 2 dimensions, 2 properties. One is the land area, one is the floor area. My vector that I get out will have 2 dimensions. So what I'm going to do is I'm going to normalize them. I'm going to take my land area, find the biggest one, which happens to be 11,780, and I'm going to divide each one of these land areas by that 11,780. So that'll give me a number from 0 to 1. So it's basically normalizing it. So you can see the 11,780 gave me 1.0, everything else gave me something else in that column. I do the same thing with the floor area. So dividing it by the biggest floor area, 3,896 gives me a different column. Okay, that's great. So I've got normalized numbers, they exist between 0 and 1. Okay, well, I said that I wanted my land area to be twice as important as my floor area. So now what I'm going to do is I'm going to weight it. So the normalized land area, to weight it, I'm just going to divide it by 2. My floor area, I'm just going to leave the same. So this column and this column are the same. And this is this divided by 2. And this forms a vector. So my vectors are this combination of weighted land, weighted floor. So vector 1 is 0.3735, comma 05996, and so on. So a vector is just 2 numbers. All right. That's great. So we now have a vector for each one of our houses. Remember when I showed you the RAG pipeline? First thing we did was take all our existing data, we ran it through an LLM, and we got a vector out. We've just done that. We are the LLM here. We need to do the same thing with our input. So we wanted a house which had 6,500 square feet of land area, 2,500 square feet of floor area, run the same algorithm. Do exactly the same what we had before, and we will get a vector out. So this vector represents our ideal house using this algorithm. Okay, so now what we want to do is find out which house is closest. There's a couple of measures of what is closest. And this is the reason I did a 2-dimensional space, because in 2-dimensional space, you and I can visualize what this looks like. When we talk about real LLMs, the one I'm using to do the embedding has 384 dimensions. I don't know about you guys, but I can't conceptualize what a 384 dimensional space looks like. So hence why I'm using 2 dimensions, because we can do this. All right. So there's 2 different dimensions. There's a couple of different algorithms to define what closeness is. The first one I'm going to talk about is Euclidean distance, which is measuring with a ruler. And the second one is called cosine similarity. So Euclidean distance. This is, we've plotted them on a graph and we've got a ruler out and we've measured the distance. It's what we would natively think as closest. So I've got my point in the middle here. I've got all these points around the outside. Smallest distance is probably A because it's the closest one to that red X. So A would be my closest distance. Now, this calculation here is the actual formula for Euclidean distance. It's basically Pythagoras' theorem extended to n dimensions. But we don't really care about the actual magnitude of the vector. All we care about is which one's biggest, or sorry, smallest in this case. So we might as well drop that square root. So you see that I'm going to start referring to squared Euclidean, and all it's doing is doing these calculations just to drop that square root to make things a bit faster. Now this is good for low dimensionality vector spaces, 2 dimensions is about as low as we can get, and it's good for text spaces. So here's the code. It's literally, 6 lines. It's just going through applying that simple algorithm. I've got this in Python in the actual code we'll look at, but it's really simple. The other one we're going to talk about is cosine similarity. Now this is a bit harder to understand. Imagine we have a point on the origin, and we are going to look at not how far away the points are, but the angle from our target vector to every other vector. So if I blow up this little point here, I'm standing on the origin here. All I care about is these angles. I don't care if it's close or far. All I care about is it's infinitely far away. What is the angle to the things that are infinitely far away? And so you can see on this one, this C vector is almost exactly co-aligned with that red X. So C is actually going to be the closest one, even though by the other distance it would be the furthest one away. Now this is slightly more complex formula, so you can see the formula given down here, given the weighted land and the weighted floor. But even then, it's still a handful of lines of code. It's really easy to calculate this stuff. Now, this cosine similarity is good for high dimensional spaces and finding the most similar text for a given document. All right, so let me look at this. I've got my 9 houses. I'm going to apply this algorithm onto each of these houses. This is my cosine similarity for my target vector, and this is my squared Euclidean for my target vector. Cosine similarity gives you a number from -1 to 1. 1 is closest, so that's the best value. So in this case, I want the biggest value. My biggest value is 0.6 at 0.9996. And squared Euclidean, you want the smallest one that's closest, which is 0.007. And if I plot those on a graph, you can see that I've got, these are the 2 results that I said. House 6 was the cosine similarity, house 9 was the squared Euclidean. House 9 is pretty close. That's our target. That is what the algorithm says that would be the best house. House 6 is terrible. It's absolutely woeful. It's got tiny land and tiny floor area. But the cosine similarity said it was best. So in this case, we wouldn't want to pick the squared Euclidean. If you remember, I said squared Euclidean was good for low dimensional spaces. Don't get smaller than 2 dimensions, so we expected that in this case. But as you go through and start these vector journeys, there's a number of things that you will find are not deterministic. Prompt engineering. There's no real science, there's a bit of science behind it, but there's a lot of art there. Playing with these similarity algorithms makes a big difference to the results you get. If you do the wrong algorithm, you get really strange results. All right. Any questions so far? You've all been very silent. I'm getting lots of nods, and I appreciate that. Any questions on anything I've covered so far? Yes?
If I heard correctly earlier, the LLM is the thing that also embeds to a vector. Is that right?
Yes.
Is that deterministic?
Yes.
Okay.
The same input. Yeah. Don't touch the mic. Does that still work? Yep. Okay. The LLM, think of it as a hash. I mean, it's not quite, but it's a similar sort of concept. So the same input will always give the same vector, given all the same inputs. So yes, it's deterministic.
Okay. I was just like, other parts of the LLM have the hallucination aspect. So it's like,
Yes. Yeah, it's the generation part that has the hallucination aspect. So remember that we've got those 2 different LLMs we're using. One is the, come back here. So this is the foundational LLM. That's the one that's generating the text output. That's the one that will hallucinate if you haven't told it to do so properly. This embedding LLM, we're not even going to give it the instructions in English. The prompt engineering is for this foundational one. This embedding LLM is the part we're going to talk about now, and I'm going to show you an example of it to generate those vectors. All right, so let's talk about the embedding model. This is an LLM. You don't need to give it a prompt. All you're going to do is, it has a job. And that job in this case is to take a piece of text and turn it into a set of numbers based on that. Now, I didn't write this. I'm nowhere near clever enough to write any of these embedding models. So I went onto a site called huggingface.co. Hugging Face has something like 300,000 models. They're free, they're open source, download, play with them. This one is small enough that I can run it on my laptop. I'm not paying anyone any services for this, and it's quite fast. So it's a really good source of getting this information and being able to play with these without having to go anywhere. The one I'm using came off Hugging Face, and it's called Sentence Transformer. It's actually the all mini LM L6v2, if you want to know the specifics. And again, the code to use this is really simple. I give it my sentence I want to transform, and I import my sentence transformer. I tell it which sentence transformer I'm using, and then I just say encode. And it's going to give me a set of numbers coming out. So again, it's not rocket science. It's really easy to get started with and play with this. So let's go and have a look at that. All right, so I have my embedder. All right, someone give me a sentence, just to make sure that I'm not pre-computing anything. This is, oops, that's not you. Tim's, oh, that's, sorry?
Are we supposed to see what you're doing?
Oh, yes, thank you.
Also,
Do you want a squishy? Good question. Okay. The aerodynamics of these things suck. Yeah.
I also want to comment, Hugging Face has lots of different transformers.
Yes.
Lots of different embedding models. Some are graphics based, some are other types of based. I don't know. Anyway, in this case, you want your sentence transformer.
Yes. Yep. No, that's a great point. So Hugging Face has all different sorts of things. If you want to do similarities on images, you can do things like the clip model. That's on Hugging Face. There's all different sorts on all different LLMs. Right. Let's see if you see that now. Right. I'm going to try again. Second time lucky. Oh, nice catch. One hand, two. Look at that. All right. All right. So someone give me a sentence. So what we're going to do is we're just going to encode a sentence. Don't all shout at once. That's a good one. Don't all shout at once. All right. And I'm just going to save that, and I'm just going to run Python embedder. And it's just going to sit there for a moment. And it's given me a set of numbers. That's literally all it is. So in this case, I've asked it how many dimensions. This model gives me a vector that has 384 components. So remember the one we used in the simple example had 2. This will give me 384 dimensions, but it doesn't matter what text I put in. I could give it a paragraph, I could give it a small amount of text. Now in this case, this particular transformer is designed for sentences, hence the name. If you give it too much text, it will chop it off at a certain point and throw the rest away. So if you do too long corpuses of information and they differ only on the last part, this is not the right transformer for you. There are other ones for you. So things like Nomic API is, we've actually got an example on our website, which I'll show you this, I'll give you a link to later, which does transformation of our documents. So we took all our documents, we scraped them, we broke them up into chunks, and we scraped them through. More than what a sentence transformer can do, we use Nomic for that one. So you take some time working out which model you want. All right. Please.
With those models, or the transformers rather, you can't, or could you mix and match those, or would it be up to you? I guess, are they compatible with each other?
No. If you want, a transformer has a purpose. It is designed to do something. So in this case, this transformer is designed to take sentences or small amounts of text and turn them into a vector of 384 dimensions. Okay? If I want to do something else with it, I've got something and I want to do image comparison on the same thing. What I would probably do is I would run it through different transformers for each purpose. Each use case has the same transformer, and then the second one I can do image searches on. I'll get different vectors out. They might be different lengths. This one happens to give me 384 dimensions. I think Nomic, you can tell how many it is. I think we're using 768 dimensions on it. So you encode with one model. So I encoded my data with all the same model. That gives me a vector. And when I compare, I must use the same algorithm that I encoded with to be able to do the comparison with, or it has no meaning.
Can I ask a quick follow-up then? So
Only if you stop asking if you can ask questions.
how could you go from a sentence then that you encode with a sentence? Is there a way that you can somehow make that give you a document? So like you could encode a sentence with one transformer, and you can encode a document with a different transformer.
Yeah.
Is there any way to, so those vectors don't go to the same database? Right?
Well, yeah, I mean, effectively, think of the vector as a column in the database. So imagine we're using business objects. I'm going to stick with business objects because what we're using here, but the same thing will apply to images and documents or whatever. So I've got a product that someone has created on our mythical bank. Okay? What I want to do is I'm going to turn that into text. I ran the sentence transformer on this, and I'll show you this in a moment. But then let's say I wanted to do another transformer for some reason. I'm going to, if it had an image, I could do an image. If I want to transform it some other way. That vector that I stored, I've put as a column in my data set. I could add another column, which is a different vector, which is a different transformer on. So if you're thinking in relational terms, we're just adding columns, and those columns happen to be numeric vectors, but the vector database will take care of that. So you can have multiple.
Thank you.
Perfect. Great questions. I'm not going to try and throw you squishy, but I'll happily give you some afterwards. Any other questions before we move on? All right. So let's look at our RAG application, because now we're going to start combining some of the stuff we've learned. We're going to look at the vectors and the LLMs, and we're going to combine them into one application. So we're going to do a RAG application flow. So this is us. This is the users. The first thing we're going to do is we're going to use that sentence transformer I just spoke about, and it's going to take my prompt and turn it into a vector. 384 dimensions, remember? I'm going to then do a vector search in the database that I'm about to show you the source code for. It's not much code, trust me. It's going to look at each of those vectors and say which ones are closest, and it will find the documents that are the closest. It will take those documents and encode them and pass that as, it'll turn them into English and to pass them into Gemini, which is my output LLM. So that plus the question that I asked and this context will go into the LLM and we'll get different results out. All right, let's have a look at some code, shall we? All right, so I've got my database. This is my whole database. It doesn't do, thank you. You know, I did this multiple times on Google Slides, and now I'm doing PowerPoint because Moov wanted me to use the Google PowerPoint. So I apologize, thank you. Anytime I do that, which will be frequently, please just remind me. Let's look at the database code. All right, so I've got my data. It's just sitting there and going to be an array. So this is not a production quality database. Please don't think it is. I'm storing everything in memory. It's just a very small data set. This for illustrative purposes only. I'm going to default my comparator to be a cosine similarity, and with cosine similarity, as we know, the larger the number is better. So I'm going to tell it how to compare the results. I'm going to go through each one of the products I have, so the 20 products I created plus the whatever ones you gave, and I'm going to call add entry. Add entry simply goes through, and put your hand up if you logged on and had a look at the little product entry. I know some of you added a product. Okay, so some of you, there's 3 fields. One is the type of product, is a savings product. One is the name of the product you give it, and one is the feature or the description of the product. So all I'm going to do is I'm going to iterate through my object, which is one of those products, and I'm going to form something where it's going to say type, savings product, name, my Griffin saving product, and then the English description. So at the end of this point, I will have an English description of that product. I'm then going to call that create embedding that we just saw the demo of, and that will give me a vector out. That's going to be saved. When I store my data, I am storing the data, that original data, because remember, we can't go from a vector back to that data. We must save that as well. And the vector, and that will allow me to search and get the data back when I do a similarity search. So, okay, that's easy. How do we do a similarity search? How do we say, out of all these vectors, which ones match? Well, I'm going to do a brute force. I'm going to go through every vector in my database and work out the similarity. So I've got my data, which has my vectors in, and I'm going to go through and look at the vector associated with this piece of data and the vector I'm being passed and compare them. Remember, the comparator in this case defaults to cosine similarity, so it's going to do a cosine similarity through them. And then all it's going to do is do an insertion sort. So I basically said I want a maximum of 5. It's going to have, say, if I don't have 5, put this in the results at this location. If I've got more than 5 and it's not in the top 5, then throw it away. So this is simply doing an insertion sort of this data. And then it's just returning that array that I've filled. So it's really, really trivial. Okay? That's my whole database. Okay?
I have another question.
Yeah.
The RAG stuff that I see generally uses something like llama index or langchain or something like that.
Yep.
This is all they're doing.
Yeah. I mean, I'm going to talk about commercial databases and where this one falls short in a moment, but fundamentally, I want you to get the concepts. You know, like, this is not rocket science. You know, but yes, fundamentally, a more complex database will have the same sort of APIs, same sort of features, but it'll do indexing that we're not covering here, and I'll talk about that indexing in a moment. Okay, so let's see this works. So the only thing I need to do to swap this over is I've got my form response no vector database I've been using. I'm going to swap it over to form response using a vector database, and all that's going to do is plug in that little database I showed you. So, a minute. There we go, turn form response. And so I'm not going to say no VectorDB, I'm going to say with a VectorDB. All right, so I've saved that. And now if I come back to my screen and reload it, all right, I'm going to ask it a question. Now remember we asked it the question before about what products do you have for griffins. See if I still have that. All right, now it has data. We are using our vector database. It's encoded those 20 products, and now it says, oh yes, I have some information. So let's check this. It should have a savings account. So I'm going savings product, and lo and behold, there is a Griffin savings account. And the description is it's high interest rates that soar as you do for Griffins. And so it has correctly identified the information. These are the 5 products. Remember we said we set 5 vectors we want out. These are the 5 products associated with those 5 things. So it's done a reasonable job saying this is specific. All right, now you guys have gone and created a data set for me. So I'm going to refresh and see how many products do we have now. Okay, kudos. You guys have done a great job, thank you. I've got probably a dozen extra products here. So I'm going to download this, and I'm going to store that in the right folder. Oops. Which goes in data. Place that. All right. So now if I come back to my application and I load those extra from CSV, so there are 9 products. So you can see the count has now gone to 29. Actually, what I'm going to do, let me prove to you that it's actually no, let's prove that it's doing that. So if I look at these, okay, I'm going to pick one at random. It's an older one, but that's okay. So the dragon scales. Who's done something fun? A leprechaun's pot of gold. Okay, so let's see if we can get gold grows best at the end of a rainbow. I'm going to copy leprechaun because I couldn't spell it if my life depended on it. All right, so we're going to come back here and go, what products do you have for leprechauns? All right, top hit was a leprechaun's pot. Okay, and it's giving me information associated with that leprechaun's pot. So, who created the leprechaun's pot? Okay, duck, sir. Sorry. All right, so we have now in real time added information in that our LLM has been able to pick up and give results on. So you remember that I said that we've got the RAG versus the fine-tuning of the LLMs. We couldn't have done this with fine-tuning. That's hard. Using RAG allows you to augment products in real time, augment information in real time, and so for things that are dynamically changing, you really want to do RAG. It adds a lot of value there. All right, any questions at the moment? All right, perfect. Presenter view, there we go. All right, so our database is simple. It's only a few lines of code. It's storing information in memory. Let's look at the drawbacks of it. Okay, we have, how many dimensions are in my vectors? Who's been listening? 384 dimensions. Very good. So, all right? So we have 384 dimensions of vectors. So even using squared Euclidean, it's going to do about 1,000 calculations. But remember we said higher dimension vectors, we want to do cosine similarity. So therefore we're doing cosine similarity. It's a more complex formula. Comparing two vectors is thousands of calculations. We only have 29. But imagine you had billions. We're brute forcing across those billions. Our GPU would melt down. It would be horrendous. So it works really well on a small data set, but you would have computational scalability as you're trying to go up to large scalabilities. The other thing is memory scalability. Each vector, each item in the vector is a float. A float is 8 bytes. Therefore, I have 384 times 8, or about 3 kilobytes of information per vector. Imagine I have 1 billion vectors. Okay, that's 1.3 terabytes of DRAM. Now, we don't have 1.3 terabytes of DRAM. That's going to get expensive. So that's a drawback. Notice our API. In my case, I've got set comparator, I've got add entry, and similarity search. Let's look at commercial vector databases. What do they offer? Computational scalability. Typically, they will use an index. We didn't put any form of an index because the indexes are complex in n-dimensional spaces. But they're going to use an algorithm called HNSW typically, and I'll talk about what that is in a little bit. But that's going to reduce the number of lookups it's going to do, the amount of calculations. However, one vector lookup could still be thousands of vector computations, and I'm just going to hold my hands behind my back so I don't hit this microphone again. It could still be, and make changing slides difficult. It still could be thousands and thousands of different lookups, retrieval of information from the database, and then the comparisons. The memory scalability in many of the commercial vector databases is still an issue. Many of these commercial vector databases will store them in DRAM, all the vectors in DRAM. And so that memory computational, the memory scalability is still an issue. Some, and I'm going to include Aerospikes in this one, store them on storage and store a reference to them. Their indexing is a cache effectively, and so it looks it up and looks it up very quickly. So in Aerospike's case, each vector requires 64 bytes of DRAM instead of 3 kilobytes. So it gives you the scalability to be able to go up to billions and trillions of vectors. I've seen there are some commercial vector databases who can reduce the quality of those vectors, and that saves them DRAM. Saves them DRAM, but the accuracy of your results drops enormously. So there's different ways of approaching this problem. The other thing to note is, look at the API. They normally do the same thing. They define an index. We didn't have to define the index API, but they've got add an entry, given a data, and a similarity search. So the API is fairly similar to what we've been using so far. They're typically very easy to get started with. If you want to see what I've been showing here but implemented against a commercial vector database using Aerospike's one, the link on the screen shows you it's the same UI. I stole it off Art at the back who wrote this UI for us. It gives the same thing, but it's tied into the Aerospike database. So it's using a real vector database behind the scenes. There's not a lot of code differences, just that database piece changes. All right, so let's talk about HNSW. HNSW stands for Hierarchical Navigatable Small Worlds. Let me assure you, after you've had a few drinks, that's not really fun to say a couple of times. All right, so if you remember, we had our house. We're going back to that two-dimensional example. We had the house and we had a whole bunch of vectors which said, these are the other houses. We had 9 houses. What if we had hundreds? Well, there's a point here at this far right. Is this going to be my closest house? Is this the one I'm going to want? We as humans would look at this and say, we can drop the outliers, can't we? We could say, I don't want this one. I clearly don't want these ones. These ones are too small. These ones are too big. These ones have too much land. These ones don't have enough land. So as humans, we can filter it down and say, well, I'm just going to focus on that part there. And so we're going to say, well, this is my good part. Now I'm going to magnify that good part. So that good part is in the middle, and I'm just going to focus on that. And then I can recurse into that and say, well, if I expand that out, so this whole graph here is just that good part expanded out, I can say I don't want any of these. They're too far away. This is the stuff I really want. Once I've got this small area down to a small number of vectors, then I can brute force it. This is exactly how an HNSW algorithm works. They have different layers. My lowest one is all my data points. As I go up, I have progressively fewer and fewer data points. And at the top levels, I have a very small number of data points. And they are spread geometrically around the n-dimensional space. So that just by traversing a few points, I can move very quickly around this space. Once I find the point that is closest to the vector I want, then I can drill down to the next layer. I get more data points, but it's localized to that point that I just found. So I can do, again, a comparison of vectors there and drop down the next layer when I find the closest one. So that process we just went through, which is implicit to us as humans, that's how an HNSW works. It's not rocket science. If anyone's familiar with the skip list concept, then a HNSW is that generalized to n dimensions. If you're not familiar with skip list as a developer, I encourage you to go and have a look at it, because I went, oh, that's kind of clever. I hadn't heard of them before I'd researched HNSWs. All right. So there's a good number of commercial databases out there. As I said, Aerospike has one. As I mentioned, we actually store the vectors inside the database. So they're always there. They're not just stored in memory. We have a caching layer that is a geometric cache on top of it. Now, that geometric cache breaks up that n-dimensional space into different regions. So this compute layer is scalable. I can add more nodes to it, and it'll break the dimensional space up into those other dimensions, into those other nodes. So it gives isolation between them and gives a fairly efficient access to the database. So this cache layer just gives access to this. It allows us to do things like self-healing. So if one of these nodes goes down, we want a fault tolerant. If either any of the database nodes goes down, it'll automatically fix it up and things like that. So it's a very practical solution. When we implemented that, what we discovered was that reads are really fast. Reads are good because you've got a steady state and you want to be able to read quickly. Writes become more of a challenge. Because you've got this big geometric index, and if you've got a database with 20 vectors, it doesn't matter. If you've got a database with 1 million or 1 billion vectors, then it starts becoming more of a challenge. If you have a reasonably high insert rate, if you lock the HNSW on each insert, you limit throughput. If you don't lock the HNSW on each write, then you have the chance of getting corruption in the index. Remember, this is a multi-layer index. And if you do something at one layer and someone else has just changed the layer above you, it might affect what you've done. And so it's not even as simple as just locking a set of records. It's not transactional like that. So this is a problem. And this is something that is very difficult to solve. So Aerospike created a solution. And we've got a patent pending on this, but it's sort of a combination of both of them. So imagine that we're inserting 1 million vectors into this HNSW. The HNSW's got 1 billion vectors in it. We're inserting another 1 million. Well, instead of locking on each write, what we're going to do is we're going to batch them up, and we're going to form local HNSWs. Remember that I said the index was partitioned geometrically. So we've got different nodes that handle different parts of this n-dimensional space. When you insert something, it puts it into a local cache on that part of the space. When it's got enough, so let's say we've got 1,000, it will form that into a single HNSW, which is local, so there's no conflict. Then it will lock the main HNSW and update the HNSW with those changes. Because it's already in an index, it's a much more efficient way of doing it. So this is designed to get better throughput. It's designed to have a more scalable, robust solution. Does have a drawback. There's always pros and cons on this stuff, in that I've cached this locally till I've formed my vectors. So if I went and did a query, as soon as I put the information into the database, it wouldn't find it. There's a configurable time period between when we get the information and when we merge it into the HNSW, so that it gives you the best of both worlds. But most people, typically with these similarity searches, you don't normally expect your results there in real time. If it takes a bit of time to get your results there, that one product, it's normally not the end of the world. Maybe something like fraud detection, it becomes more important. But most use cases, certainly the one we've been doing today, if it took me 5 minutes to get that product there, it wouldn't matter. Does that all make sense? All right. So let's talk about vector databases in fintech. There's 2 parts of vector databases we've spoken about. One is similarity search. This is just that embedding of vectors and moving it and doing a comparison. So I can do this standalone. I don't need an LLM to be able to do, I don't need an output LLM to be able to format text. We've happened to do an example of this, but imagine we're doing a shopping cart, and we're doing similarity searches. You're looking at a pair of sneakers. You might also be interested in the socks to go with the sneakers. It's a similarity search, something which is around that product. I don't need an LLM to produce an output. I just need to know what products are similar to that product. So that's what we're focusing on now, is that similarity search piece. So where would we use this in financial services? Something like fraud detection is an obvious case. I've got a set of known good transactions that have occurred. I've got another vector that represents a transaction coming in. It's very, very similar to the other vectors that I've seen. And therefore, I'm going to say it's almost certainly a good one. If it's an outlier, if it's a long way away from those other good ones, then it's quite possibly fraud. And I want to spend more time investigating it. Now, one thing I didn't necessarily show is when you're doing the similarity search in the vector database, remember I said I'm doing an insertion sort? That means that I know how far away they are. I have to do that to do the insertion sort. So you can get out how close are two vectors to each other. Give me the 5 closest ones and how far away were they. If they're really close, then that's a good thing. Okay? Obviously, search capabilities. If I'm doing vector search, I can do extra searches and say, these things have more relevance to what you're searching for. It can be structured or unstructured. So at the moment, we all tend to do searches across things that are exact. I'm looking for this person's name. I'm looking for a product. But what if someone misspelled my surname? My surname's a bit funky. People misspell it all the time. If everything else matches, then why shouldn't it be the same person? If I encoded my details as a vector and compared the vectors, then it would pick up more fuzzy matches as well as exact matches. Things like transaction identification. I have my credit card statement. I want it grouped by financial things like hotel bills, airfare bills, things like that, but at the end of the financial year. But I want more flexibility than natively comes with my credit card providers. I can do that using similarity search. So there's a bunch of things where similarity search can really help in fintech. Okay? We're all used to, well, certainly, before I started getting into this world, I'm used to exact matches. I'm doing something and it's an exact match. Now, that exact match might come out of I'm looking up someone's name or a graph traversal, but in any case, it's exact. Similarity searches are, this is closest, this is really close to what you're doing. It's a new way of doing it. It would be rare if I wasn't doing a chatbot to have a vector database as my only vector database, as my only database in my application. I still need things that are exact. I still need to be able to look at my products and my accounts and people's balances. That has to be exact. So quite often you'll find that people either have multiple databases, vector databases and relational, or they might have one multi-model database which stores all the information but has a vector search capability as well as storage capabilities. So that's similarity search. We've also got the RAG, the Retrieval-Augmented Generation. How are we going to use this to help fintech? And there's a lot of things. Obviously, chatbots is one. As I mentioned, we're doing a chatbot on our website, so you'll be able to ask anything across the website and it'll quite happily give you an answer. But things about personal recommendations. Look at me as a person, my goals, my products, know what's out there in terms of what other things are out there, and do a comparison. Generate a result out of that and print out financial services reports or something like that, which will say, here's an investment strategy tailored to you. Takes away from the human doing it. Human would still review it, but it takes a lot of that drudgery out. So there are multiple reasons you might want to use something like RAG in fintech. So this is just a list that I came up with, but I'm sure you guys have different domains, different expertise, and I'd love to hear any ideas that you guys had about where else you might use RAG in this. All right. Couple of things, just as I said, I work for Aerospike. If you're interested, we have a community. It's a community forum, and it's staffed by developers, people like myself, like Art at the back there. We're nerds. We're not here to sell or do anything, but if you're interested in vector databases or getting started or anything like that, we'd love to hear from you. So that's a QR code on the left. If you want to get started and play with the commercial one for free, the Aerospike has free trials, so you can go and play with the one on the right, and see what you think. Any questions? Yes?
So when you do similarity
So you want, I'm not sure I understand. So you've got, what are you doing a similarity search on? A person? Or?
So for example, you're doing similarity search on merchants.
Yep.
And the merchants have two different names.
Yep.
Like X and Twitter.
Yep.
They're essentially the same entity, but they have different names.
Okay, so that's a great question. So there's a couple of different ways. So the question was, if you've got merchants who have similar name or different names, but they're the same sort of entity, like X and Twitter, how do you make them the same? There's a couple of ways of doing it. The first is the vector encodings that we've shown are standard open source ones. You could create custom ones, you could fine tune an LLM for that specific case. I probably wouldn't go to that, but if it's something that you're occurring regularly, what I would probably do is I would combine a vector database with a graph database. So I would have vectors for both X and Twitter, but then I would have them linked in a graph. And so when I go in, quite often we'll find that vector and graph are fairly tied together. If you think about a knowledge graph, you would do a search for some term, in your case it's a company, but that information will be linked to other things, and you want to form a result based on that conglomeration of information. So you might do a vector search to find a starting point in a graph, and then traverse the graph to find out who is this really. And then you can use an LM to take that output and turn it into meaningful results. So yeah, the multi-model extends more than just traditional databases and vector, but yeah.
The follow-up question will be, so you would go with using, say, X embedding to find X in your graph database, and then use the link between X and Twitter to find Twitter.
Yeah, that would be one way of doing it. Now, something like that, because it's an alias, maybe not. Maybe I would just put something in and have the company name as one of the fields, but everything else as something else. And everything else would match except for the company name. So that would be very close vectors. But if it's something which is slightly more broad and it's not just that one case of a rename, but it's an identity graph or something like that, then yes, I'd combine vector and graph. Great question. I got more squishies. Does anyone want me to play squishies at them? You know I'm missing squishies? The aerodynamics on these is terrible. Oh, the chivalry of the chicken. All right, who else? All right. The last thing I'm going to say is thank you. You've been a great audience. I've really appreciated the interaction. I hope this was useful. I'd love any feedback. On your Moov application, or sorry, your FinTech DevCon application, there is a feedback form. I'd love any feedback, positive or negative. I just want to improve so that, I spoke last year, I spoke this year. I enjoy these sort of conferences because they're nerd to nerd. No offense, I'm a nerd. I think it's, it's great. So any questions, we're here. We actually have a booth upstairs if you want to drop by and say hi. We'll be there for the whole show. But thank you. Really appreciate everyone.